as we take a look at principal components analysis, we realize that we've taken a major step towards data reduction, right? So in our context of the serials, the first two principal components were the most significant by far. In fact, if we take a look at those, we will see that the eigenvalues for PC1 and PC2 constitute 95.45% of the entire set of the entire variance in the data. And so PC3, 4, and 5 contribute very little, and therefore we considered those principal components to be negligible. Now, so we've basically taken 5 things and reduced it down to 2 things. And so that's data reduction. But it turns out that we could actually take this 5-dimensional data, and given that there are 2 principal components that are dominant here, I mean, a lot of times this will be the case. I mean, sometimes you may have several other PCs that contribute, but one helpful thing is because PC1 is going to contribute more, going to absorb sort of more of the variance than PC2, which will absorb more of the variance than PC3, we could always take a look at what's called a score plot between the first 2 principal components, or between any pair of them for that matter. And so we now have a 2-dimensional plot of our data where each point on this plot represents one serial, and its location in this 2-dimensional space indicates how it scores, what its score is on PC1 and what its score is on PC2. So for instance, if we look at protein O's, you can see that on the PC1 axis, okay, this axis from left to right is the PC1 axis, and the axis runs up and down is the PC2 axis. So protein O's, if you look at this, has somewhere just slightly above a -3 score on PC1, and it has roughly a, what would we say, slight negative on PC2 as well. All right, well, to better understand what this means and how this is going to help us, it might make sense to just take a look at the big picture of classifying these. So recall what PC1 and PC2 represented. We said that PC1, we could sort of think about the quote-unquote healthiness of the cereal. And as sugar content increases, and then it seems like important nutrients decrease. So we could flip that. We could say that as nutrient scores increase, sugar content decreases. Okay, in a similar fashion. So for PC1, we see that it has a far left-leaning PC1. It has a highly negative PC1. Now, if you look at the components of PC1 that could contribute negatively to that value, you would have things like calories, fiber, protein, and sodium. Those all contribute negatively to the principal component score, whereas sugar is going to contribute positively to that. So given that it has a high negative score, it is either high in calories, fiber, protein, or sodium, or some combination of those. Well, as it turns out, protein O's are, not surprisingly, high in protein. And so because they're high in protein, that contributes to a highly negative score. Now, if you can recall, none of these are super salty cereals or super high caloric cereals. If we scroll back up, I mean, there's a vast range of them, but it's not like, some of them are 500 and 700. But nonetheless, the calories do contribute as well. We'll just see that maybe not as much as we might think. PC2 we sort of described as, well, this is a contrast between calories, sugar, sodium, and contrasting, I guess, technically fiber and protein. So you would have a negative score on PC2 if you tended to have either high fiber or high protein or high fiber and high protein, right? And so the cereal is actually high in protein, and because it's protein O's. And it is actually, let's see, pretty good in fiber as well, right? It's one of the higher fiber cereals. So that's probably why we, maybe it doesn't have a ton of fiber, but it contributes to a slight negative in protein O. So we can see that each of these classifications, so if you're high in PC1, you're going to tend to be more sugary. If you're high in PC2, well, that means you're going to have either high calories, high sugar, and high sodium, right? So it's going to have lots of these different nutrients in them. So notice that these scores, we can kind of break this up into 4 quadrants. We have the upper right that are sugary and nutrient dense. Okay, that's how maybe we'll describe it here. Nutrient can be like sodium, calories. Those aren't necessarily bad things, right? Lower right, if you think about it, well, it's still sugary because it's high on PC1. It's positive on PC1, but it's negative on PC2. And so those are going to tend to be lighter cereals, right? Lighter cereals in the sense that if they have a high negative value for PC2, they're not going to have a lot of sugar, calories, or sodium. They're just going to have a lot of fiber and protein. So that's what we mean by light cereal. Upper left, okay, so if we're to the left of this line, well, that means we're scoring negative on PC1. So we can kind of classify that as healthier, right? If you think about it, Nutty Granola sounds healthy. Fiber Crunch, Protein O's, Bran Delight, probably pretty healthy cereals just based on the name, but you can't just go by the name, of course. And protein dense if it's in the upper left, right? Because we just, some of these words are a little odd, I guess, when we think about it, because Protein O's are protein dense as well. But let's look at Nutty Granola and see where Nutty Granola scores. Okay, Nutty Granola scores, yeah, pretty high on the protein as well as Protein O's. The reason, though, Protein O's maybe has a negative on PC2, let me think here. Upper left, okay. So actually, I guess we could kind of say, Protein O's has high protein as well because of PC1. Nutty Granola is kind of high because of its contribution by PC2 or to PC2. And fiber focus, so Protein O's and Fiber Crunch. Well, why does this make sense? Why can we describe it this way? Well, it turns out that there's a very intuitive mathematical answer once we get past a little bit of mathematics to understand how these scores are calculated. Okay, so let's make the following claim. If you have a symmetric matrix, which we do, remember that covariances, correlations, whether you talk about variable 1 compared to variable 2 or variable 2 compared to variable 1, you get the same answer. If we went back up and looked at those matrices, we would see that they are symmetric. And a symmetric matrix will have orthogonal eigenvectors, which, by the way, we can make into orthonormal just by, because remember, we can scale an eigenvector by any constant and it's still, by any non-zero constant, and it's still a valid eigenvector. Okay, and so with that said, that's a very important piece of information that will help us. Now, to get a score for a given PC, we have what it actually means, like how the PC is computed. Well, recall that the principal component maximizes the sum of squared. Okay, so we square the orthogonally projected distances of the points on the given eigenvectors to the origin. Okay, that's how we compute this. So let me give you an example of, here I just have some centered, we'll just pretend like it's standardized values, and what we would do is if the red line were one of the principal components, we would project all of these points onto that, right, orthogonally. So each of these angles would be 90 degrees, and this guy's angle would be 90 degrees, and this guy kind of falls on the line almost, 90 degrees, 90 degrees, and 90 degrees. Okay, and now if you take a look at variability, the variability falls between here and here. And so, you can kind of think about this interval as representing the variance of those points compared to that line, right? But look at this blue line. This blue line's better because notice that if you project orthogonally all of these points onto this line, notice how the variability is, at least visually, hopefully it looks visually more variable. Look at the length of this blue box that I'm drawing and compare it to this one. It's, I would say, clearly a little bit longer, right? There's more variability in this direction than there is in this direction. Now we would, compute the distance between each point and the origin. So for example, this guy here, for this point, its distance would be this entire length to the origin, and then we would square that. Okay, so that's what we mean, the sum of the squared orthogonally projected distances of each point to the origin. It's a mouthful. Okay, so the question is, how do we project? Well, we're not going to get into the derivation of this, but to project a point or vector, right? Point and vector are interchangeable, onto another vector, u, is given by, okay, this is how we read it, the projection of y down onto u equals the dot product between y and u over the dot product between u and u. Recall that this is a scalar. You get a dot product. This is a scalar. And when you divide two scalars, you get a scalar. So all we're doing is we're scaling the u vector by that amount. And its magnitude, remember we use absolute value for that, that just means the magnitude of something, would be the magnitude of that quantity, which, by the way, since this is just a scalar, it does not itself have any length, but it will multiply the length of u. So notice how it kind of can get pulled out, because scalar doesn't have a length. It has a length of 0. Okay, so let's imagine that here is our vector y, and we want to project that down onto vector u. Okay, now down onto is relative, but here I want to write this projection right here. Okay, and that point that I get of that 90-degree projection right here, this new point, or vector if you want to call it that, which I am going to refer to that as the projection of y down onto u. Okay, sometimes you might call that y hat, put a little hat over it. That vector, that black vector right there, is the projection of y down onto u. Okay? So that's the visual I want you to think about. Now let's put this into context of projecting our point, a point y, down onto one of our orthonormal PCs. Now, so in our case, u is what we're actually going to be calling v1 here. Okay, so v1 is actually vector u in this diagram over here. And so, okay, mathematically, its distance, the projection of y down onto v1, okay, its magnitude, because that's what we care about, right? Its length, and we're going to get its squared length, technically. Though I'm not really going to worry about that, because that's just for maximizing the sum of the square distances. If I just want to know what is the PC's score, right, I am going to figure out how far away from the origin that point is. So let me write this down. And that is precisely what we mean by the PC1 score of y. Okay, so that's what we're referring to here, and that's what we see in that two-dimensional graph where we plotted PC1 against PC2 for each of our serials. So each of these serial is going to get a score. It's going to get a amount of distance to move from the origin along PC1 and along PC2. Excellent. Okay, we're almost there. So what will this look like? Well, according to our sort of template formula here, it will be y dotted with v1, y dotted with v1 over v1 dotted with v1, multiplied by the length of what we're projecting down onto, which will be v1. Okay, now a couple of really cool things happen here. Recall that the magnitude of a vector, I'm using x just to point out this, it will be the dot product of the vector with itself square rooted. Okay, that is the magnitude. So if we square this, if we were to square this, the square distance would be x dotted with x, right? We cancel out the square root. So if that's going to help me here in a moment. What's the length of V1? Well, it is an orthonormal vector, so it is going to have a length of 1 in this context. That's not true of all vectors u that we're projecting down onto. It's just true in our context. That's why I said let's put this into context for us. Now, if the length of V1 is 1, i.e. the square root of V1 dotted with V1, then what would be the square of that value? Well, the square of that value would also be 1, which means that V1 dotted with V1 is equal to 1 as well. Okay, and now that really comes down to just taking the dot product between the point and the vector. So the projection, the length of that projection, i.e. the PC1 score, would just be the dot product between the vector or the serial and the corresponding eigenvector. So for any given data vector y, we have that its score on the ith PC, okay? So depending on how many principal components we have, we'll have 1 up to d, the number of variables that we have. We could technically score on each of the PCs, but we're only picking the dominant ones, the ones that contribute to the most, that contribute maximally to the variance. Yes, and so now the projection of our point or serial onto the corresponding principal component will be the dot product between the serial and the corresponding eigenvector. Sweet. Okay, so we are almost there. Now recall that what we're actually using is the data in standardized form. So we've centered the data and we've divided by the standard deviation. So don't be surprised when you see a negative sugar score here. That just means that for protein O's, it scores, it's 1.34 standard deviations below the mean. 1.34 standard deviations below the mean. And all that says is that it is less sugary than some of the other cereals, right? So you can have a negative score in that context. Scores much higher on protein than most of the cereals, a little bit higher on sodium, slightly higher on calories, and pretty high on fiber as well. Now V1, which again is orthonormal, if you were to compute the length of this thing, you would get 1. It's orthogonal to the other eigenvectors, but it is length 1. Now look at what happens when we take the dot product. It'll be the first component times the first component. Well, how is that going to contribute to the score? It's going to contribute negatively, right? That's going to be a negative contribution. So what does that mean? Well, it means that for calories, it actually scores lower than, it scores a little bit higher than the average. And on this one, we'll also get a negative contribution. But notice that the size of this, it'll be a little bit of a greater negative contribution. So I'll just do negative and then an up arrow, because notice that negative 1.34, it is well below the sugariness of some of the other cereals. And the principal component here is positive, so it will decrease its principal component score just a little bit more. Here we are high in fiber. We have a negative PC1 score. That's going to have a negative contribution. Here, again, a negative contribution, positive 2 points. It's really high in protein. This is a very negative score. Now remember, as we said that here, as sugar goes up, these other nutrients go down. So the fact that it's having a lot of negative contributions is actually indicating that it's probably a slightly healthier cereal, right? We can't take it verbatim because it might be a little bit more calorie dense, but it's also very low in sugar, which makes it contribute negatively to that principal component 1 score. And again, we have a negative contributor here because we are higher in sodium. So you can see that this is pretty nutrient dense, so to speak, as we might say. So where are we? Protein O's, healthy and fiber focused. So having a negative score on PC1 is actually probably a better thing than having a positive score, because a positive score will often come from having a high amount of sugar, right? If principal component 1 doesn't change, it's going to remain positive 0.4158. The only thing that can change from one cereal to the next are the standardized scores. So if a cereal is really high in sugar, then that's going to be a very positive number. Multiplied by a positive number would mean the second term contributes very positively. Maybe it's also high in calories, so that could also bring that score down a little bit because it's multiplying a negative value. But then it's probably really low on protein, right? So if it's really low on protein, much lower than some of the healthier cereals, then it's going to multiply a negative by a negative. That's going to have a positive contribution. And so you can see that our statements line up with what we observed. And I wanted you to see this because just telling a person that upper right represents sugary and nutrient dense. Again, maybe these aren't the best words to use here, because what do I mean by nutrients? Sodium, I guess, would technically be a nutrient. Calories, I don't know if those are nutrients. But anyway, these are just some of the words that we could use to describe this. And notice that we can classify all of our cereals into this graph, which gives us powerful information about which cereal we should choose. So we're going to be choosing Fiber Crunch, Bran Delight, Protein O's, more likely than we would, something like Cinnamon Swirls if we were focusing on being health conscious.